discuss spinor representations of Lorentz group in a little more detail. And we'll also make contact with what you all know. How do you study Dirac Fermions in the kinds of notations that you study and the way I have described them here. So, spinor notations. Of Lorentz group. You would have studied Dirac Fermions as 4-component objects, but we'll write them in terms of 2-component objects, made up of 2 components objects, and therefore 4-component versus 2-component notations for the spinors. So like we said, a Dirac fermion is a 4-dimensional reducible representation. So a Dirac fermion is a 4-dimensional representation of reducible representation of Lorentz group. 4-dimension means it's made of 4 complex components. The generators, Lorentz generators, for this representation is constructed in terms of 4 gamma matrices. Gamma mu. What gamma mu satisfies? The algebra. The name to this algebra, sometimes people call it Clifford algebra, is twice eta mu nu. Do I have a minus sign there? No. So each one is a 4 cross 4 matrix. There are 4 gammas, and each one is a 4 cross 4 matrix. Gamma mu times gamma nu plus gamma nu times gamma mu is twice eta mu nu, and eta mu nu was our diagonal with minus 1. Is that what I have? No, plus 1. Plus 1, minus 1, minus 1, minus 1. Since these are 4 cross 4 matrices, there is also a unit matrix sitting here, 4 cross 4, which very often we won't write, but we'll always understand it's there, because it's a matrix equation. And the Lorentz generators for this representation contain the orbital part plus spin part. And the spin part is given by sigma mu nu is half commutator of gamma mu and gamma nu. This is how you would have seen it. Now these gamma mu matrices, 4 cross 4 matrices, which satisfy this algebra, Clifford algebra of gamma matrices, Dirac matrices, can be written in many equivalent representations. So gamma mu's can be written many equivalent representations. And they are related to each other through similarity transformation. Similarity transformation, take a matrix A inverse gamma mu A. So if gamma mu satisfy this algebra, so do A inverse gamma mu A. You can check it for yourself. So we can use this property of this algebra to write gamma mu's in any convenient form that we want to, we think for our purpose is convenient. One such form is called Weil basis. One basis is called Weil basis. And Weil basis has a special property that the chirality matrix gamma 5 I, let me see if I have the sign proper, that's a minus I, gamma 0, gamma 1, gamma 2, gamma 3, product of all the gammas is diagonal. So that's the nice property of Weil representation. And how do gamma mu's look like in Weil representation? So gamma mu is a 4 cross 4 matrix. So A runs from 1, 2, 3, 4, and B also runs from 1, 2, 3, 4. We'll write it in 2 cross 2 blocks. Diagonal block 0, 2 cross 2 block, and here sigma mu and here sigma bar mu, and we label the components of this 2 cross 2 block here as alpha and alpha dot down, alpha and alpha dot down, and this one beta dot beta up. Now here alpha takes values 1 and 2, so does beta. Alpha dot takes values 1 dot, 2 dot, and beta dot also takes 1 dot, 2 dot. There is a special way of labeling these 2 by 2 components. First one we call it undotted index down alpha. Second one dotted alpha dot. Same way for sigma bar. First one beta dot up and beta. Now what are these sigma mu's? Sigma mu, these are 4 2 cross 2 matrices. Sigma 0 is a unit matrix, 2 cross 2 unit matrix. And sigma 1, 2, 3 are ordinary poly matrices. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. And sigma 3 is 1, 0, 0, minus 1. So that is this block. Sigma 0 is a 1 cross 1 unit matrix, 2 cross 2 unit matrix, and 3 poly matrices. And sigma mu bar is again the first sigma 0 is a 2 cross 2 unit matrix, and minus sigma I, the 3 poly matrices. Is that clear? Now, if I write my gamma matrix, which satisfies this Kleber algebra in this particular way, then I can now ask the question, what is the algebra for the sigmas? So, this algebra then breaks into sigma mu bar plus sigma mu bar is twice eta mu. Now, if I keep track of components, sigma mu was this way. So, as a matrix, this is a matrix, 2 cross 2 matrix, alpha down, beta up, later is the second index. And sigma mu bar, sigma nu plus sigma nu bar, sigma mu. This is also 2 eta mu nu. And if I want to keep track of the matrix labeling, now this is alpha dot up, beta dot down, later second index, alpha dot, beta dot. So, this algebra of Dirac gamma matrices breaks into 2 sets. The first one has an unbarred sigma, barred sigma, unbarred sigma, barred sigma, and mu nu interchanged. Second one has barred first, unbarred second, barred first, second, unbarred. And like we said, that in this basis chirality matrix gamma 5 is diagonal. So, let us evaluate gamma 5 with this. And if you evaluate gamma 5, which is minus I, gamma 0, gamma 1, gamma 2, gamma 3, it's a 2 cross 2 block unit matrix here, 0, 2 cross 2, minus 2 cross 2. So, gamma 5 has broken into block diagonal form with the unit matrix here and minus unit matrix here. So, if I want to pick up the left-handed and the right-handed projections of a Dirac fermion, I do that through the projection operators. So, the left-handed projection operator is 1/2 unit matrix. This is 4 cross 4 unit matrix. I will be using the same symbol from context, you should be able to figure it out. Huh? This is a 4 cross 4 unit matrix, this was a 2 cross 2 unit matrix here, plus gamma 5, and that is unit matrix. Now, here it is a 2 cross 2 unit matrix. And the right projection so what it tells me is that if I project a 4 component Dirac matrix through a left projection to pick up the left component part of the Dirac matrix, all that will appear is the first 2 components of the Dirac fermion. And if I want to project the right one, then it will have the lower 2 components of the Dirac fermion. So, which means in this basis what we have done, we have placed the left part of the Dirac fermion in the upper 2 components, and right part of the Dirac fermion in the lower 2 components. Now, what happens to the Lorentz generators? the sigma mu nu's. So sigma mu nu, which we had defined as I by 2, so Lorentz generators. Commutator of gamma mu, gamma nu. This also breaks into a block diagonal form. Sigma mu nu, 2 cross 2, 0, 0, sigma mu nu bar, where sigma mu nu is I by 2 sigma mu bar minus sigma mu bar, and sigma mu bar is I by 2 sigma bar mu bar sigma mu. Clear? Is that now Lorentz transformation also break into block diagonal form, where sigma mu nu is this one, and if I want to keep track of matrix first and second, starting from the way we defined that we labeled them, sigma unbarred were labeled with first undotted, second dotted. The lower ones, these were labeled with first dotted, second undotted. So it would have first undotted and second undotted. The dotted ones would be contracted. Similarly here, so this appears with the first dotted up, second undotted. This is first down undotted. So this is then alpha dot first, beta dot. And you can check now is that this object is nothing but a Hermitian conjugate of that. This has many properties, but one nice property is that trace of sigma mu nu and sigma bar mu nu is 0. Trace is in the matrix trace, not in mu nu, which is, what does it mean? Sigma mu nu alpha is 0, sigma bar mu nu alpha dot is 0. For every one of these sigmas. And that is a very nice property. We'll see why that's a nice property. They have another nice property. Sigma mu nu is self-dual. What does that mean? That sigma mu nu is same as 1/2 I half epsilon mu nu alpha beta sigma alpha beta. The two are equal. So this property, there is a name, we give a name to it, that's self-dual. This operation of multiplying by epsilon mu nu alpha beta I by 2, we call duality change. So if something under duality is itself, we call it self-dual. And sigma mu nu bar is anti-self-dual. That is, sigma mu nu bar is same as minus I by 2 epsilon mu nu alpha beta sigma bar alpha beta. So what is this? That in what have we done? We have done is that we have chosen a very convenient basis for Dirac matrices in terms of these sigma mu's and sigma mu bars, so that the Lorentz generators break into a diagonal form where the first block is self-dual, second block is anti-self-dual. Is it clear? And does that make contact with what we said earlier? We said any antisymmetric tensor, two-index tensor, under the way we said under the Lorentz group, behaves like the self-dual part behaves like 1-0 representation, and anti-self-dual part behaves like 0-1 representation. What we have done is we essentially have broken Lorentz generators in those two forms. So what does it mean? It means that Lorentz group that we had earlier studied could be written, the algebra of the generators of Lorentz group could be written in terms of two SU2s. For the spinor representations, we have broken those, explicitly demonstrated what those SU2s are. Because the two SU2s are generated by, one by this sigma mu nu, another by this sigma bar mu nu. A few minutes later, we'll see exactly how that connection is also in terms of how do we understand generators of SU2, how is this generator of an SU2. But before I do that, let me list some properties or other properties of this which may be useful in calculations at some stage if you want to do some calculations. So these are some identities. If I take sigma mu nu and sigma lambda rho, this can be written as mu lambda rho mu nu antisymmetrized minus I epsilon mu nu lambda rho minus I delta lambda mu sigma nu rho lambda rho. These square brackets mean antisymmetrization of indices. And there is a corresponding one for bar. And sigma lambda sigma bar mu nu is I times delta lambda mu sigma nu minus epsilon lambda mu nu rho sigma rho sigma bar mu nu sigma bar lambda minus I delta lambda mu sigma bar sigma bar lambda sigma mu is I delta lambda mu sigma bar mu plus epsilon lambda mu mu rho sigma bar rho So if you want, you can check them. But if you feel lazy, don't worry. But at least check the next one, because that's a lot more useful. So this is an exercise. You can convert barred sigmas into unbarred by the following trick. Take the barred alpha dot alpha is same as epsilon alpha dot beta dot epsilon alpha beta sigma mu beta beta dot and sigma mu alpha alpha dot is alpha beta alpha dot beta dot sigma bar beta dot beta. So exercise this, check this one. But what are these epsilon symbols that I've introduced? I introduced epsilon 4 index, which we understand, right? Now I introduce epsilon 2 index with these dotted and undotted indices. So epsilon 1, 2 is same as epsilon 2, 1 and it's the same as plus 1 and that is same as minus epsilon 1, 2 and that is same as plus epsilon 2, 1. Epsilon 1, 2 up, so epsilon alpha beta is an antisymmetric matrix, 2 plus 2 matrix. Up and down are each other's inverse. So similarly for dotted ones, 1, 2 is same as epsilon 2, 1 dot is same as 1, same as minus epsilon 1 dot 2 dot, same as epsilon 2 dot 1 dot. Or let me write it in matrix form. Epsilon alpha beta is 0, 1, minus 1, 0. And there is another nice compact way of writing it, which is useful. So I'll write that. It's same as I sigma 2, the second Pauli matrix, right? It's the same as the second I times second Pauli matrix. And its inverse, alpha beta down, is 0, 1, minus 1. The inverse of this matrix is this. Is that correct? No, I didn't change the sign. This. Transpose of that, and that is minus I times sigma 2 Pauli matrix. And alpha dot beta dot with dotted indices is also 0, 1, 0, minus 1, 0, and that is I sigma 2 alpha dot beta dot. And inverse of this matrix is also same Is that clear? And now, using these definitions, it's very straightforward to prove this. Provided you notice, use the identity. I'll give you a hint also. Use the identity that sigma 2 times any one of the three poly matrices 1, 2, 3 is nothing but minus times sigma that poly matrix transpose. Just check this identity first and then use that identity to prove the first one. This is very simple. If sigma is 1, sigma 2 and sigma 1 anti-commute. So, sigma 2 square is 1. So, it is minus sigma 1 and transpose of sigma 1 is itself. So, that is minus sigma 1. Right. If it is sigma 2, then sigma 2 times sigma 2 is 1. So, it is sigma 2 here. But sigma 2 transpose is minus sigma 2. So, that takes care of this side. Now, the same sigma 3. So, this is a straightforward identity. Anyway, before I go further, I have used these indices alpha, beta and mu nu. So, I will just make a general statement about this labeling. In our notation, we shall use early dotted or undotted letters, or early letters I should write here, early letters dotted or undotted of Greek alphabet for spinor indices. That's alpha, beta, gamma, alpha dot, beta dot, gamma. Mostly, I think we shall mostly use mostly. Some places I may do otherwise, but from the context it will be clear. Very rarely I'll do that, but from the context it will be clear. And later letters for space-time labels. That is mu, nu, lambda, rho. So because we have so many things around, so let's make this distinction. So now that we have understood how to, in this basis, write the Lorentz generators for 4-component spinors, Dirac spinors, and they break into block diagonal form, this one and this one. And we also saw that, so that now Dirac fermion we shall write it as the 4-component Dirac fermion with A is equal to 1, 2, 3, 4. As the first 2 components, we'll call them small psi, and label the components by index alpha. alpha takes values 1 and 2, spinor index, and a lower component, we'll call it chi bar, and label its components by alpha dot up, alpha down, alpha dot up. So we have written now these 4 components in these 2 components, we call them psi, and those generators, the first block will act on these 2 components, the second block will act on these components. And these 2 components, these 2 psi's and chi bar, correspond to half 0 and 0 half representation of the Lorentz group. This is corresponding to one SU2, this is corresponding to the other SU2. SU2 spin representation is 2-dimensional, spin half. So it has only 2 components. This is 2 complex components. This one has 2 complex components. And now, if I use these projection operators, what does that do? PL on psi is 1, 1, 1. So let me write it explicitly again, is half 1 plus gamma phi times psi, that picks up psi alpha up, and P right psi is half 1 minus gamma phi psi Now let's try to figure out how do these objects transform under Lorentz transformations. What would he say? That Dirac fermion transforms under Lorentz transformations. Lorentz through a matrix U of theta, we call it psi prime of x is U of theta psi U inverse x, where U theta is exponential I by 2 theta mu nu times the generators. So generator is the capital sigma mu nu. And when I write these sigmas in the block diagonal form, this breaks up into a block diagonal form, small u theta 0 0 u theta bar. And like we said, the first two components of this would transform according to this law. That is, half zero representation is that psi alpha will transform as psi alpha prime, which is u theta alpha beta psi beta, and that is exponential minus I by 4 theta mu nu sigma mu nu alpha beta psi beta. And the lower two components of the Dirac fermion would transform as chi bar alpha dot to chi bar prime alpha dot is u bar theta alpha beta, no, alpha dot beta dot chi bar beta, and that is exponential minus I by 4 theta mu nu sigma bar mu nu alpha dot beta dot chi bar beta dot. So that's what the transformation rules for upper two components and the lower two components become. It's a straightforward to check. We said that this object is conjugate of this. And if you check it, then you can rewrite this as the following way. Exponential, or you can rewrite this as u theta dagger inverse alpha dot beta dot. Somewhere, I think, no, it's still there. This property, that this object is dagger of that, tell you is that you can rewrite this as, in terms of this u, as u dagger inverse, u dagger because sigma is u dagger inverse, and inverse because of, if you take the dagger of this whole thing, this will change sign. So that you put inverse there. So this is now how these objects transform. Let's look at these transformations in a little more detail and to make contact with what we had discussed in earlier lectures and see how these are really the transformations of half zero and zero half representations. Oh, I just rubbed off this part. But from the definition of sigma mu nu, sigma 0 I would be I by 2, sigma 0, sigma bar I minus sigma I, sigma 0 bar. That's the definition. Sigma 0 is a unit matrix. Sigma bar I is a minus polymatrix matrix. These two are same, so you have minus sigma I by sigma I polymatrices. Similarly, if you do sigma ij, you will discover this is ijk, sigma k polymatrix. I think no sign there. Is there a sign there? No sign there. And then remember, we had defined theta 0 I, we had renamed that theta 0 I at some stage as minus phi I. and theta ij as minus epsilon ij k alpha k, the transmission parameters. Now let me take this object, what this object is, 1 by 4 theta mu nu sigma mu nu. I can write this as 1/2 theta 0 I sigma well, I have done, let me keep the way I have done it in my notes, 0 I plus 1 by 4 theta ij sigma ij. This object is minus pi I, this is pi I, so that gives me I by 2 pi I sigma I. Put this in it and this in it. There are two epsilons, contract them, that will give you a factor of 2. 1 by 4 will become 2, and then it is 1 by 2 alpha I sigma I. Let me make sure that I have the sign right. No, I have the sign wrong. You'll check it, then there's a minus here. And that is because I think in this definition there's a minus here. So this is phi I. And then what do we have here? We have minus I by 4 theta mu nu sigma mu nu, and that is I alpha I minus I phi I, okay, call it k sigma k by 2. So that tells me u theta is exponential of I alpha k I pi k sigma k by 2. Now you recognize there is a generator of SU2 on spinners. That's how we wrote it. And I can rewrite this as exponential I alpha k minus I alpha k call this mk. And similarly, u bar theta alpha k plus I phi k sigma k by 2 exponential I alpha k plus I phi k n k. And when we discussed the spin half representation of Lorentz group, we said precisely the generators are sigma k by 2. And this is a transformation parameter, as opposed to real SU2D. Here we have them as complex transformation parameters. And this is the one we had called M, and this is generators of other SU2 we had called N. That's why I use the same symbols M and N. So that tells us what we were saying. I mean, this is nothing but a restatement of what we were saying earlier, is that Dirac fermion is a sum of half zero and 0/2 representations of Lorentz group, where half zero representation transforms according to this rule or according to this method. This is equivalent way, as a doublet of the first SU2. See, this object lives in the first SU2. So as a doublet of the first SU2, and the lower two components, which is 0/2, transform as a doublet under this SU2. Now these small u's have some nice properties. U theta and U bar theta are unimodular. That is, determinant of U theta is 1 and determinant of U bar theta is 1. And that is very straightforward to see, is because determinant U theta, I can write it as exponential of trace log U theta. That's the way determinants are. Product of all the eigenvalues. So this is what it is, product of all the eigenvalues. A determinant of a matrix U is exponential of trace log U theta. And that is exponential of trace log U is minus I by 4. Is that what it is? Theta mu nu, sigma mu nu. And the trace is now, it's in the spinor space. The trace of each sigma mu nu we said is 0. So this is 0. So this was one way of writing determinant of epsilon. There's another way of U theta. There's another way of writing explicit definition of determinant of a 2 cross 2 matrix is 1/2 epsilon beta epsilon delta gamma delta epsilon alpha beta epsilon gamma delta of U alpha something is not right. Yes, this should have been alpha beta gamma delta alpha gamma U beta delta. That's the definition of determinant for a 2 cross 2 matrix. There's a nice identity for these epsilons, epsilon alpha beta times epsilon gamma delta is delta alpha beta gamma delta anti-symmetrized, which is delta alpha delta beta gamma delta minus delta alpha delta beta delta gamma. It's a nice property of these two cross 2 matrices. Use this property and the definition of determinant. Now this object is equal to 1. The determinant U is 1. Use this property to show the following thing, that epsilon alpha beta can be written in terms of U alpha gamma, U beta delta times L. This is a very nice property. Does anybody recognize what this says? We learnt on 2 spinors, to do Lorentz transformation, you multiply with a U. So a 2 spinor index beta. So what have I done on the right hand side? this is a two-spinner index. This is another two-spinner index. For each one of them, I multiply by u. This is the Lorentz transformation of symbol epsilon alpha beta. So what this equation tells me is symbol epsilon alpha beta is Lorentz invariant. Clear? This one. This one. Is there an overall minus sign? I don't think so. Somebody has an idea, yes. Determinant of is minus 1. The determinant of epsilon is minus 1? Oh, no. Determinant of epsilon is 1, right? Okay, if there is a sign error, correct it. But this is the property you want. Yes, I think you are right. There should be a minus here. But anyway, the master property is this. And similarly, if you do it, you can, for upper ones, and for undotted ones similarly. And similar one for so what does it tell us? These epsilon symbols are Lorentz invariant. And since epsilon symbols are Lorentz invariant, they can be used to lower or raise the spinor indices on any object we have. This is the same reason why we use eta mu nu to lower the space-time indices or raise the space-time indices, is because eta mu nu is invariant under Lorentz transformations. So these objects and the inverse alpha beta and dotted ones are Lorentz invariant in the same fashion as eta mu nu is Lorentz invariant. Does not change in Lorentz transformations. And we use eta mu nu to raise and lower indices on the space-time indices. Same way, use epsilon alpha beta, and epsilon alpha dot, beta dot, to raise or lower the spinor indices. In particular, see, we had defined Psi is with lower index beta, the upper two components of the Dirac fermion. If I multiply it by psi up alpha, or conversely, psi alpha down would be alpha beta psi beta. And we have defined chi beta dot, the lower two components of the Dirac fermion. And if I want to raise or the inverse I have rubbed off that portion part, but we know how psi alpha down transforms by just multiplication of u small u. Let's check it out how psi alpha up transforms now under Lorentz transformation. So psi alpha up goes to psi alpha prime, and psi alpha prime I can write it as epsilon alpha beta psi prime beta down, because by the rule of raising and lowering I just multiplied by an epsilon, get it back to this, and for this I have already prescribed my transformation rule and used that. Now I have used rho in my notes, so this is one place where I have used rho for a spinor index, because I have earlier said I'll keep rho for the space-time. So this is one exception. So that's what the transformation law is. Now let me raise this up again. Now another exercise. Show that U inverse alpha beta is same as epsilon beta sigma U sigma rho epsilon rho alpha. You will be able to show this quickly if you use another identity, which is sigma mu nu alpha beta can be written as minus epsilon beta sigma sigma mu nu sigma rho epsilon rho alpha. Take the sigma, multiply by 2 epsilons on two sides. Keep the rule of contractions that lower down, upper down, down, and interchange alpha beta. That is the same as this one. Just take component 0i, ij, and check this is true. If this is true, then this is follows straight forward. What does this tell me? That this object is U inverse lambda alpha psi lambda. Just from the definition, we define upper through this contraction, upper index psi alpha through this contraction, use the transformation properties of what psi down is, raise this lower to up again, and use the identity that this object is nothing but u inverse lambda. If you do the same exercise for now psi bar, chi bar alpha dot down goes to chi bar prime alpha dot down, and use alpha dot beta dot right. Right, like this. And this transformation property, we have prescribed this transformation property, and that was, this is alpha dot beta dot. Check your notes, u dagger inverse beta dot rho dot chi bar dot rho dot. And rewrite this as epsilon bar b bar u dagger inverse and a corresponding identity here for u replaced by u dagger, both sides. I'll give you an answer. Now, what is the point of doing this exercise? The point of doing the exercise is this immediately tells us now how to write Lorentz invariant products of representations. For example, now, this immediately will tell me that psi alpha, take a two-spinner psi alpha, take another two-spinner chi alpha is Lorentz invariant, because it transforms into psi bar, psi prime alpha, chi prime alpha. Psi prime transforms as psi lambda u lambda inverse lambda alpha. Chi transforms as alpha rho chi rho. U and u dagger is 1. Is that clear? So this gives us a method of writing Lorentz invariant bilinears of spinners. And in order to write, what is the rule we have followed? First one with index up, second one with index down. This one we prescribed the rule for transformation earlier. This one we worked out what it is here, and then this is Lorentz invariant. Similarly, take so now a spinner corresponding to the second SU2, psi bar, with a lower index alpha dot, and another spinner in the same representation of same SU2, chi bar with an index alpha, is a Lorentz invariant, because this one and this one transform in opposite way, u and u dagger. Is that clear? Now, this is a slightly different way of writing Lorentz invariance than the 4-component notations that you have had. If you, how would you have written a 4-component Lorentz scalar? Psi bar, psi. What is bar? Psi dagger, gamma 0. Is that clear? This is what you normally would have done. But what we have done is we have done it, written as the same thing in different notation. Because if you work it out the way we defined, psi was defined to be psi alpha, chi bar alpha dot. And gamma naught is sigma naught and sigma bar naught. That's what how in our basis, and that is use these things and figure out that this product is nothing but psi alpha dot chi alpha, psi bar alpha dot down, chi bar alpha dot. So this, and when you take Hermitian conjugate, that will become psi bar, and Hermitian conjugation under Hermitian conjugate half zero representation goes to 0 half representations, so you relabel the index alpha dot, because that transforms under second SU2. This is what it is. This is Lorentz invariant, this is Lorentz invariant. Now we'll use a somewhat very often used compact notation. For psi alpha chi alpha, we'll just simply write psi chi. Right? It's a compact notation, but by writing psi chi, what we mean? Psi alpha up, chi down. Now, does it matter if I change the order? It doesn't matter if I change the order if psi and chi are anti-commuting spinors. How do I see that? Psi alpha up is alpha beta, psi beta, chi alpha. By definition, lower it. Now, if interchange these objects, because they are anti-commuting spinors. So, if I interchange these two, I change sign. Now, write this as beta alpha chi alpha psi beta. Interchange alpha beta index, that takes this out. Now, this is the rule of raising for us is epsilon beta alpha chi alpha. This is chi up. And that is same in our short notation. Clear? That psi chi is same as chi psi. And similarly, shorthand notation for psi bar chi bar is psi bar alpha down, alpha up. Now see the difference between definitions here. Psi and chi is contraction with first up, second down. And this psi bar chi bar contraction is with the first down and second up. This is the rule. When you make contractions with the undotted ones, you go from up to down. When you make contractions with dotted ones, you go from down to up. Some people wave hands and says one of them is like this, another one is like this. Or like, no, one of them is up down and the other one is like this. So this is the rule. Undotted up down, dotted down up. Once you get used to it, this is, I'm going slowly over it because this is something one has to get used to. Even now I do mistakes sometimes. So we have 10 minutes more. Let me do one more thing. So now we understand how a Dirac fermion is in half zero and 0 half composite representation of the Lorentz group. Now let me go back to saying that we said P mu or vector A mu or P mu is in half zero half half representation of Lorentz group. Four independent components. How do I see that P mu 4 vector in this representation, in this way of writing it? So P mu as a bispinner. So we write P mu and multiply it by sigma mu alpha alpha dot, because that's how we define sigma mu, those 4 2 cross 2 matrices, and we index them first undotted, second dotted, lower. Take this product. So we have converted the 4 vector P mu into a bispinner by multiplying by sigma mu. And this object, because it has an undotted index here and dotted index, transforms under Lorentz transformation as a doublet under first SU2, as a doublet in second SU2. Is that clear? Explicitly we see now how these 4 components of P mu nu can be written as 2 cross 2 matrix, whereas the first label is for first SU2, second label is for the second SU2. And as a 2 cross 2 matrix, what does it look like? P0 plus P3, P1 minus IP2, P1 plus IP2, P0 minus P3. So the 4 real components of P mu live in this bispinner representation as P0 plus P3, P1 minus IP2, P1 plus IP2, P0 minus P3. These 2 components transform as doublet of first SU2. These 2 components transform as doublet of second SU2. Clear? Now the last point I want to discuss is that how do we understand charge conjugation in this language? You would have studied charge, how do Dirac fermions transform under charge conjugation. How does charge conjugation act on a fermion? Psi under charge conjugation goes to psi c, and psi c is the charge. Well, let me write a component also. This C is not a component, this is charge conjugation. This is a component A, 4 component, times a charge conjugation matrix AB times psi bar transpose B. That's the definition of charge conjugation. The 4 Dirac spinner goes to transforms the charge conjugate is a charge conjugation matrix times psi bar transpose. And charge conjugation matrix is I times gamma 0, gamma 2. So, and what does this look like? In our basis, while basis, because we're choosing we have the while basis. Put gamma 0 to be sigma bar is minus, right? So this is identity, this is identity. This is what it is. Take the product, and what does this look like? This is in while basis. So now let's break this into components. So charge conjugate of A is the charge conjugation matrix I sigma 2 minus 0, 0, I sigma 2 psi dagger. Oh, psi dagger is sorry, psi bar is psi dagger gamma 0. Use the same definitions again, and let me write down psi here first. Take the dagger of this, multiply by gamma naught in the while basis, and you will discover that the answer is the following: chi alpha psi bar alpha dot. Conjugation makes this psi bar and this into chi. Bar is conjugation. And this gamma naught interchanges them. So then therefore here it is chi alpha psi bar alpha dot. Or I call this beta dot here and beta here. So that is I sigma 2 alpha beta chi beta I sigma 2 alpha dot beta dot psi beta dot. This times this, this times this. And I've just put indices now, alpha beta, beta, beta. Now I times epsilon alpha beta, I times sigma 2 is epsilon alpha beta. And this is epsilon alpha dot beta dot psi beta dot. And that is, this lowers this and this raises it. So what does charge conjugation do now in our language? Charge conjugation, the 4 Dirac goes to 4 Dirac conjugate. And 4 Dirac here was psi alpha down, chi alpha dot up, goes into chi alpha That's what charge conjugation does now. It converts psi alpha into chi alpha and chi bar alpha into psi bar. It converts particle into an antiparticle. That's what charge conjugation is supposed to do. Clear? Now, there is a class of fermions called Majorana fermions. By definition, Majorana fermion is a self-conjugate fermion. It's its own conjugate. Dirac fermion is made up of an electron and a positron. So, there is a particle and an antiparticle. Majorana fermions are their own antiparticles. So, a Majorana fermion is when psi is psi conjugate. So, unlike Dirac fermion, they cannot carry charge because they are self-conjugate. So, for a Majorana fermion under charge conjugation, what does that tell me? That Majorana fermion chi alpha is same as psi alpha. So, a Majorana fermion is psi alpha times same psi, take a complex conjugate. The lower components are only complex conjugate of the upper component. They are not independent. Dirac fermions, we wrote a symbol chi for them. There are two independent components. So, Majorana fermion, unlike Dirac fermion, has only two independent complex components. Dirac fermion would have two in the upper two components and two in the lower two components. Two in the psi, two in the chi. I think with that we'll stop today, and we'll, with this much of labor about how to write representations of Lorentz group, spinor representation of Lorentz group in this language, we are ready now to set up supersymmetric algebra. That we'll do next time.